Hello and welcome everybody to day 17 of Advent of Code. This is being recorded on day 18 of Advent of Code, and if you've been following these day by day in real time, you'll also find there is no video for day 16, and that is because day 16 broke me. I was able to get the part 1 solved, but then the mental leaps required for the part 2, I couldn't get it done. I haven't had a chance to go back to actually look at it. I did look at day 17, which was pretty fun. I more or less had the full thing solved yesterday evening, but life took over. I had other things to do, so I couldn't actually get the star finished and then record the video, I set that as kind of a requirement that if I get the 2 stars done, I can record the video on it so that I can reliably talk about what it is. It's being recorded now on the morning of day 18. I'm going to go through what I did and hopefully, have a bit of fun. I say day 16 broke me. It did a bit. I've had a bit of a crazy last couple of days, so might be a bit patchy going forward on this, but I'm going to try. If I can get a day fully finished, I'll still put a video out for it, but the streak is broken. Oh well, I always said we'll see how long we can last. Turns out the 15-day streak was the best I can do this year, so I'm going to keep doing this. Maybe next year I'll do it again and maybe I'll get the whole thing. Who knows? Or maybe I won't. Maybe it'll be even worse. Anyway, let's dive into day 17. So, day 17, pyroclastic flow. So what are we doing? We're going through our tunnels with our elephants, because why not? And eventually the tunnel has opened out into this very tall, narrow chamber. And there are oddly shaped falling rocks coming down this chamber. You can see the shapes of them here listed out. We're told there's only 5 different shapes of rock, and these are all of them. So they're falling one after another, one at a time. So once one falls down, it comes to rest, and then the next one falls, and it always follows this pattern. So the order of them always stays the same. What else have we got? So then our actual input to the problem is this line here. So the arrows denote the direction of a jet of hot gas that's going to push the rock 1 unit to the left or right. So every time the rock moves down 1, it gets pushed either left or right, and then it moves down 1 and it gets pushed either left or right based on the pattern of these jets of gas. We're told that the chamber is exactly 7 units wide, and we suppose it's infinitely tall, really, for the purposes of our problem. So they've got a little animation here of how the rocks would fall. So here's our first one ready to go. The jet of gas pushes it to the right. Now, once it's next to a wall, it's not going to get pushed any further, so it just falls down one, until there ends up being a jet of gas that wants to push it to the right. So it pushes it to the right, but now we're down at the very bottom, so it just settles down at the very bottom. And that's that rock settled, it's at rest. So now the next type of rock gets dropped, which we can see is this guy here, and that matches the second one in this list, and that'll keep going. But what's important as well is that as these keep going in a cycle, your jets of gas also keep running in a cycle, so they just keep looping over and over again. So there's just an example of how this pattern plays out as the rocks fall down. So after a certain number of iterations, you end up with a rock pattern that looks like this. So our job basically is to simulate this, more or less. So the elephants want you to simulate this. So they want to know how tall this tower is going to end up after you've dropped 2022 rocks, which I've just realized is the current year. I don't know why that just dawned on me in my head. I was like, that's an odd number. I wonder if that has something to do with the problem. And now I think it actually doesn't. It's just the current year. Wow. Yeah, well done, Ian. Okay, so anyway, with the simulation, you do your simulation and you want to see how many rocks fall. All right, so let's look at the code. First thing I'll say is my code is real spaghetti-y for like just getting the simulation to work. And that's just because I wrote it kind of organically. Like I wrote one rule and then I wrote the next rule and then I wrote the next rule and then tried to simulate it each time on the screen to then make sure I was getting the rules right. So it's a little bit thrown together, but it does work. It does satisfy all the conditions and actually simulates it correctly. So what do I do? Yeah, first thing I did, I create this static map basically of all the rocks. So for each point on the rock, what I've done is I've just decided, so basically this is the definition for the rock. It has a hard-coded height and width because we know what the height and width of our rocks are. And it also has this hash that lets you define every single point of the rock. So these lambda functions, you pass in an x and a y coordinate and it'll tell you what the translated point is that matches to a part of that rock. So I've decided that there's a reference point on each rock and it's the most bottom left point. So what that means is we're told that every time a rock falls, it falls from this coordinate here. That's where it starts at, is the most low left point on the rock. Starts at 2 in from the side and 3 up from whatever the bottom is, or the highest point that we've achieved in the tower so far is. So I reasoned that from here I can make a coordinate space that defines the entire rock, each rock on it. So the first one is, for most of them, the first one is this xy, so it's just that point, and then each rock is just a translation based around that. So if I have some coordinate, maybe 4, 5, I can know that, okay, the first point is 4, 5, so then the next point is 4 and 6, 4 and 7, 4 and 8, and that makes me make a line of points that are stayed together. Just some convenient stuff in here so that the translations can be made a bit easier. Most of them are pretty straightforward in terms of there's always one point on it. The only one that doesn't have that is the cross-shaped point, where this point in free space is your reference point. That's what's going to start at the point the 2 in and 3 up is always going to start there, so that doesn't actually feature in the point at all. So you pass in the x and y coordinates and that's actually just a translation, all of them. So yeah, I defined that's static. We'll just close that up then. We'll use that later on. So basically we're told an amount of loops that we want to look at, which is, in our case, it's 2002 is what we want. This number doesn't match here because of just some, this will be apparent why I changed this loop number for the second part. But anyway, for the first part, that would just be the amount of times you're going to loop through. So it's basically the amount of rocks you're going to simulate falling. Now, some stuff to do, some things. So I basically, these all have indexes, each rock 1 to 5. To make those work in a loop, I have a counter of how many rocks have fallen, and I just do a mod 5 operation each time to get me the next one in a sequence that will always be reliable. You have to do some zero checking here because you can't mod by a 0 index or anything like that. So this works out. Or sorry, if you get mod 0, I want to return index 5. Otherwise, I just do the mod operation. So we're going to get into basically an infinite loop here of moves in a second. So we need a way of breaking out of that, which I have. So this tells me if the rock is now at rest. I'll talk about the window size in a minute. That's an optimization that I made after the fact. So my initial approach, I just scaled an arbitrary sized grid, started at the bottom and started filling in rocks as you went up, which was fine. It worked grand. I think it needed about 5,000, a height of 5,000 or something like that, and then it pretty much was able to it was, oh no, well, it can't be a height of 5,000. What was the height? Oh yeah, the grid height, it was, what's it, something like 3,500 or something like that, because that was my answer. Yes, so it just needed to be more than that. I think I initially put in like what was it, like 10,000, and just it worked. It didn't overflow, so I was like, that was fine. But for the second part, they effectively do their usual trick of meaning that you couldn't possibly fit it all in one memory space. So I figured I'd have to change that. But anyway, as we go through it, So I have a convenience method down here, which gets me all of the points for any rock type given an initial xy, which is down here. So it basically loops through that static array, calls the points function for an x and a y coordinate, and gives me a new set of points coordinates, which all match where the rock should be. Then I need to do a couple of things. So first thing I do is I render that rock and I print it out on screen. Then you need to check whether the rock's going to move left or right based on the jet of gas. So I do the same mod trick here, just slightly different, but basically the same thing, so that I know wherever I am in the sequence, once I've hit the end of the sequence, I'll just loop back around to the start again and keep going. This isn't based on how many rocks have fallen though, it's based on how many moves have been made, which is effectively this inner loop as well. So every time a rock moves either left or right or down, every time a rock has moved down one space, that counts as a move, and you'll move on to the next like jet of gas to push it. So that's all that is. So yeah, basically using that, I have some checking logic in here, which I'm not going to go into in any real detail, but basically all it does is it determines whether my current points, if I translated them left or right, whether they'll either go off the edge, positive or negative, or whether they'll hit an existing rock that's there. If that's the case, then we just don't move it. If we're hard up against either an existing rock or an edge, we won't move left or right. That's all this logic is checking. And then there's more or less the same thing for going down the way. So this is now we increment like a y value to go down one, and we're going to do similar checks. If we're already at the bottom, we're not going to move it, but we're going to exit instead. Or if any point on our rock that's falling is going to touch another rock, then we're going to exit as well. And that's it. We get down to the bottom, and we get down to the bottom, yeah. And now the only thing at the bottom is we also need to record what our height is that we've reached. So if you drop one flat rock and it goes all the way down to the bottom, the previous height was 0. Now the highest point is 1 unit or whatever. And then say as another one falls down and ends up maybe it's 3 high. Now the highest point is 4. So when our next rock drops, it drops 3 higher than 4, and then it goes down. But there is also a case where, say, if I have one here that's 3 high and then one of 2 landed beside it, the height of that isn't the highest point. This is still the highest point, so we still drop from just above that one. So yeah, I'll talk about the windowing function now because it makes a bit more sense. So previously we were just adding stacks and stacks and stacks all the way up, and the array would just keep growing. But that doesn't really scale very well. So instead, what I've done is I've made basically a window. So the window is, you can imagine, we're just preserving a certain window of the entire stack as we go. It does have to have a certain height, because I was thinking I could just do like 5 or 6 high and then just drop the bottom few rows and add some fresh blank rows up on top each time. But the thing is that sometimes in your perspective of the window, sometimes it'll be valid for the rock to actually fall down the bottom of the window and fully leave the gap here. But the thing is, you actually don't know. So it could, if it fully leaves and fully left, it's fine. It didn't change anything. But what could happen is it could come down and stop here, so that some of it's still above the line. Because you don't have anything saved, you actually would lose that, and it would appear to just drop, or it would hit the bottom and it would be sticking up where it shouldn't be sticking up. So I preserved some trial and error. I just kind of preserved a window height that's sort of seemed to work in most cases. So for me, I use 100. So it means I'm only ever saving 100 spaces. And that seems to be enough that you don't have stuff falling off the edges where it shouldn't be or anything like that. Okay, so window function, yep, to have the windowing function, and I'm able to, so yeah, then the biggest height, this is just a bit of messing you have to do then with a windowed function to get the biggest height, because your biggest height, you have to basically, you can't have it just overflow the size of the array now, but you need to maintain the actual value of the biggest height, because the biggest height now only is a reference to inside this windowed function, so it has to be a number between 0 and 100. So I keep a rolling sum then to keep track of that. So effectively, you just want the difference between the last height and the most recent height you've managed to get to. So that's it. It's a bit convoluted, but let's run our 17.1. And did I comment that out? Yeah, so I'm running the visualization here, so it'll run kind of slowly, but you can see it. And there we go. So there's our rocks falling down. You can see the pattern as they go. So this is just the standard simulation. We haven't reached the top of our, our window yet. So we're getting there. We'll start at some point. I have a limit set so they can only go so high before it hits the breaking condition. And now I think it should do it in a second. It's probably gone a bit off screen because I don't have enough screen real estate to render it here. But in a second it should. Oh, maybe it isn't. Maybe I broke something. Or maybe it's just still crunching. It should start chunking down the way. If I move this down. Oh, it's still going. Huh, that's weird. Why isn't that? Oh, how much am I rendering? Oh, that's why. Now I know what's going on there. So I changed my window height. Let me kill this. And I'll just try and make a smaller window so you can see it easier. Yeah, maybe that'll work. So I made a smaller window. So it should now start to refresh and reload the visualization. Struggling for words this morning. It's kind of early. Come on, baby. Let's do it. Hey, there we go. So now you'll see the bottom is shifted down as we start reaching the top. So we've reached the top there. So the next one, it shifts down. And that's our window function. So this will just keep running until it calculates up to the top. Okay, I'll kill that there. So I thought that might be a good enough optimization to totally solve the second part. But then for the second part, they basically ask you to do the exact same thing. No change to what the problem actually is, except they want you to run it for this ungodly number, which is that a trillion? I don't know. Maybe it's a trillion. Who knows? It's a big number. So anyway, they want you to run it for this many loops, and you can't do that. Even though this solution, so it's artificially slowed down here for the simulation. If I remove the visualization, it should run. I'll bump that back up to 100. It should run quite quickly. Yeah, so it runs very, very quickly. Now let's just put this up to what it should be as well, the 2022 or 2023 even. Yeah, so it runs very quickly. But even though that runs quite quickly, it still isn't gonna complete in my lifetime if I try to do this 1 trillion times. So you can't do that. So the clue then, as happens with a lot of these, is that it's not really a clue. It's sort of a leap you have to make. Is that there's probably some sort of cyclical element in here. Oh, there's a cat wanting to come in. Come on. Hi. So the whole cyclical element will probably crop up where basically you don't need to actually simulate it over and over and over again, because once you've reached a certain depth of simulation, you're probably going to start hitting cycles in it. So what you need to do is you just need to find where the cycles are, and then you can just do some maths to compute what the answer should be. So in my case, I set an arbitrary loop count of about 4,000 times to try and identify the loop. And then so it's the exact same code as before. The only thing I've added is to define where I'm finding a loop. I bet you basically need some sort of, cache to figure out if I've seen this current game state before. So what I did in here was I create a cache key, and the cache key is a little bit difficult maybe to explain, but essentially it's like the surface of this. So it's each relative, so it's from the highest point, each relative height of all of my 7 cells, and then you combine that with the current rock type shape you're on and the index where you are in your jets of gas. So if you see that pattern multiple times repeating, and you're able to record at what height that occurs, at what amount of rocks that occurs at, and what height those are, you can then work out mathematically what your answer should be. So let me run. I can run my part 2 code, and you'll see what I mean by the pattern. So that's run a bunch of times. I'm now just in a debugging window, so I can look at my cache. So this is my cache, so these are my cache keys, and then beside it is a value that's the number of iterations and the height. So for the sample, you see here, this cache key has appeared a lot. So in my head, that looks like that's a loop to me. And it is. This turns out to be what the actual loop is for the cycle. So it first starts at 28, and then it repeats every 35 rocks on from there. The initial height was 49 after those 28 loops, but now it's going to add, I think, is it 60 or so? No, it's not quite. It's like 57 or something like that. It's going to add each time, which it does. So it adds that number 57 or so each time onto this height. So with that amount of information, you can pretty much solve this with maths, which is what I do down here. I just wrote it in comments because I did it in the terminal window here, as opposed to actually writing code to just do it automatically, because it was a bit of inference involved in me looking at the numbers. So yeah, these are the numbers from maybe I'll do that. Maybe I'll do it with my my input instead. And it should be down a bit further. Is it? Where is it? Oh, it's down a good bit further, but we'll get there. Yeah, there we go. So here we started into our cycle. So this is probably not enough loops to 100% guarantee that this is a global cycle. It turns out it is, but the more you run this, the more loops you go through. I did 4,000 just so it would run pretty quickly, but the more you do it, the larger this list will grow, and then once you have a very large list, you're probably pretty certain. That's not 100% a guarantee, but it's a heuristic that was good enough for this. So yeah, we know our initial steps. We got that here, 197. We know the height at that point. Hello. So then we figure out the cycle length. So the gap between 197 and 1942 and 3687 is 1745. And the height differences again, and this is the consistent height difference that each block will achieve, is 2753. So you can figure out now how many full loops of that will fit into your 1 trillion. You take away the amount of loops you've done from the 1 trillion divided by the cycle length, and that gives you a number of full loops that you're going to go through. And then the full loops, the height then becomes the full loops times the height, the size of the height cycle. Then you just need to know one more piece of information, and that's that you're probably not evenly dividing into it, so you're going to end up with a remainder. So I'll do the mod operation here to figure out what my remainder amount is. And then you need to figure out what the height for that remainder is. So in this case, the remainder I got was 800 and something, which means you need to calculate the height that it will have achieved at the whatever that number is above 197. And then that number you add into the height at the end, and that gives you your final answer. And that's it. Now, I had all the bones of this done. I had the cache and everything done yesterday evening with hours and hours to spare. But just doing this calculation was breaking my brain at the time, and I ran out of time to do it, and I had to go out, and I was going out for dinner and doing all sorts of other things, so I just didn't get this bit of calculation done until first thing this morning. I did the calculation and the answer turned out to be the right answer. So I hope that explanation was good. I hope you guys understood what I was what I was yammering on about there. And yeah, I'm gonna go and start. I'm gonna look at day 19. So you may see my pretty smiling face again later on today, or you might not. You might never see it again. But anyway, this is day 17. Yeah. So I'm gonna have a look at day 18 now. And anyway, I'll see you guys later.